Welcome back. In the last lecture, we started discussing statistical mechanics. We will continue that discussion. Today we will start with partition functions for independent particles. So, what is first independent particles? Okay, that is the particles that do not in any way interact or associate with other molecules. Okay. We will consider two cases, one is distinguishable, another is indistinguishable. So, distinguishable particles are the particles that can be differentiated from each other. Now, which essentially you can imagine that the particle could be some way labeled, that is red or blue, or kept at a fixed position, example particle in a crystal lattice, and you can know exactly which particle it is. But in practice, the molecular system are mostly indistinguishable particle if the particles are of same type, and that is what we consider. Another case here, the particles that cannot be differentiated from each other are called indistinguishable particles. These particles can interchange locations, so you cannot tell which particle is which. That is typically the gas particles, they move around and hence they can interchange positions. So, we will be considering model system to appreciate this understanding. Okay. So, let us assume that a model system has energy levels E j, okay, and j of course will vary. The system consists of two independent subsystems with energy E I and E m, and we are considering independent particles, and we are also going to consider distinguishable particles. Let the systems A and B, we are going to label the systems A and B, because A and B corresponds to two independent subsystems. So, imagine that you have a system which you can separate as A and B, okay, and in such a way that they are independent, and hence you can just focus on the energy levels, simply summing up, okay, for each energy levels can be summed up as subsystems energy levels, okay. Simply E j is small e I of system A and this is of system B subsystem, where I can vary and m can vary from 1 to B, I can vary from 1 to A. Now, given this, you know that given this you can calculate the partition function for each subsystem. Partition function for A would be simply this, summing out from 1 to A, because I varies from 1 to A, and B would be simply this, where we are summing up the Boltzmann factor from 1 to B. Okay. Now, if you want to find out the entire system partition function of the entire system, we will be simply summing up the Boltzmann factor, where this single summation will be replaced by double summation by replacing E j as E I A plus E I B, and I will vary from 1 to A, m will vary from 1 to B. Now, considering this to be independent, you can segregate this, okay, and then since this is, you know, because of the independent, you can separate it out in this way and this way, and this is nothing but Q A and Q B, okay, because this summation has nothing to do with I, and this one has nothing to do with m here. Okay. So, considering the independent, independent particles, you can simply write Q as a simple partition function, multiplication of the partition function of subsystems. Now, if there are many subsystems, or if you are considering n independent and distinguishable particles, okay, then you can extend this exercise and you can write Q 1 to n here, which essentially means since they are independent and distinguishable and of the same type, and hence each of them will be same, and thus you can write simply Q to the power n. Okay, this is what we are going to consider. Otherwise, you can simply write as Q 1 to Q n. Okay, now let us consider the complexity when you cannot segregate as a distinguishable particle. Okay, so let us consider in that case. So, when the particles are indistinguishable, okay, then you cannot put any labels A and B because the particles are not distinguishable. So, though the energy of the system will still be like this, but you cannot segregate. Okay. So, you can write out this E as this, and here I can also vary from, let us say, 1 to T1 and this 1 to T2, but the summation no longer can be separated. In that, as a result, what you have done is you are going to overcount the summation by a factor of 2 factorial for this 2 particle system. In that case, you have to divide this by 2 factorial, but for n indistinguishable particle, the partition function in this case can simply be q to the power n divided by n factorial. N factorial comes because of the overcounting of the summation, because you cannot segregate or separate it out, the summation. So, this turns out to be the case for indistinguishable particle partition function, okay, for n particle system of same type. Okay, so with this we can now extend and try to understand how do we calculate energy, internal energy from the Boltzmann distribution. Okay. So, in our original analysis we postulated that the energy can be given by simply average of E, and it will be simply the first moment of the probability distribution weighted by first moment of probability distribution, which is nothing but summation of Pj Ej. Now, we can replace Pj by e to the power minus beta Ej divided by q, which can be written in this way. Now, let me so what we have introduced here is beta, which is nothing but 1 by kT, okay, which is written here. Now, if you take the derivative of this partition function del q by del beta, it turns out that this is nothing but, if you take it, the Ej comes out here, it is nothing but this part. Okay. Now, if you compare these two terms here, it appears that you can write this expression u as simply minus 1 by q del q by del beta, or in other word minus del ln q by del beta. Okay. So, this is a simple way, simpler or compact way of this expression which we have calculated. In terms of energy, also in terms of temperature, you can write this as, you can replace beta by kT, 1 by kT, and then this you can show that u is nothing but kT square del ln q by del t. For the case of an independent particle, I can write an independent distinguishable particle, I can write q is equal to q by n. Okay. So, for case of an indistinguishable particle, we will be writing q n by n factorial. Okay. So, for the case of this, which is independent and distinguishable particle, this is q, and then I can find out what is the average energy u by n, average energy per particle. We can plug in here this expression, okay, or in the other case, okay, and this can be shown to be in this way. Okay. Similarly, I can write entropy. Okay, you can plug in P here in this way, and this can be shown to follow this expression. Okay. Similarly, you can extend this exercise, you can write u as in this form, you can show that F is nothing but minus kT ln q, which basically relates the free energy to the macroscopic property of the partition function, and sometimes called the bridge equation. Now, without deriving in detail all of it, we can summarize this expression in this way, where we have written the macroscopic or thermodynamic properties to the microscopic properties of the partition function. Okay. So, this relates u to q, s to q, f to q, chemical potential to q, pressure to q, and this is a very useful relations to connect to the molecular informations to the thermodynamic properties, and this is sometimes also used in molecular simulation to evaluate thermodynamic properties. Okay. Now, having this information, you can also apply to many different cases, many different examples. Schottky two-state model is a classical one. So, here I will not go through the how to solve this problem, but this is a typical problem which you can try to attempt. So, here you consider a system that has n independent and distinguishable particle, that means you do not have to worry about dividing by the overcounting. So, it will be simply q to the power n, okay, the partition function, and it has two energy level for each particle, a ground energy state with 0 particle and an excited state with epsilon 0, which means q is nothing but 1 plus e to the power minus epsilon 0 by k T. Now, determine the average particle energy. Of course, you can calculate this, okay, which is u by n, okay. And this is something which we have done it earlier. This is what we can use. Q we plug into e to the n, and q is here 1 plus e to the power minus epsilon 0 by k T, and from here you can obtain the expression u by n, which is going to be average E. Okay. Similarly, you can try to get heat capacity, entropy, free energy per particle from all this exercise and using the expressions here. Okay. Okay, and this is a typical expressions which turns out to be as a function of the temperature, which you can show that this indeed is directly from these calculations. Okay. So, as I said, without going into details, you are welcome to do this exercise. This will help you to further appreciate the molecular information or pictures, or how to evaluate the thermodynamic properties from statistical mechanics principles. Okay. Okay, so now I am going to extend this exercise and summarize what is an ensemble. Now, this is something which we commonly use to connect to the macroscopic properties. So, let me just first define ensemble. Ensemble is the collection of all possible macrostates or snapshots of the arrangement of a system. Ensemble is also used to describe the constraint placed on a system. So, what are the typical common ensemble? Canonical ensemble, where we keep TVN constant. Isobaric isothermal ensemble, where we keep NPT constant, okay, and grand canonical ensemble, where we keep TV mu, that means chemical potential constant. Macro canonical ensemble, which is a common the ensemble where basically energy, volume, and N is constant as far as the expressions are concerned. But from the experimental point of view, these two are the most commonly used in experimental conditions, and that is why we need to know how to evaluate the probability distribution in these two ensemble. Okay. Or so, as I said, if you want to find out the probability distribution, we have to minimize the relevant thermodynamic property, as we have done for Helmholtz free energy. For the case of NVT, we found the Boltzmann distribution as the probability distribution for that e to the minus beta E divided by Q. For the case of NPT, we have to also consider other constraints and use Lagrange multiplier to solve it. Let me first try to explain the macrocanonical ensemble, and then we can try other ensemble. So, macrocanonical ensemble is nothing but an isolated ensemble, because energy is fixed. Okay. And the important thing is it is not connected to any thermal pressure or particle bath. So, macrocanonical ensemble is qualitatively different from other ensemble, because it involves no fluctuation of any extensive property across the boundary. So, the equilibrium property distribution is obtained by finding the probability that maximize the entropy with the constraint that the probability sum to 1. That is something which we have already done in the last lecture. Okay, and remember that we have tried to use Lagrange multiplier method, where we have used ds is equal to this expression, where we have used the maximization of entropy with just one constraint, which is this, okay, where summation of Pi is equal to 1, and this expression satisfies the fact that this is nothing 1 by T, the number of energy levels, or the number of degeneracy W here, okay, the maximum way of arranging the particle having a constant energy E. Now, you can extend these exercises for grand canonical ensemble. So, as I said, I am not going to go into the details. So, grand canonical ensemble describes a system with a dithermal, rigid and permeable wall. So, it allows the fluctuation. So, basically there is a heat bath across the system, and as well as the particle bath. So, the system is at constant volume connected to heat and particle bath. To obtain the appropriate potential function at T V mu, we need Legendre transformation from the Helmholtz free energy. Okay. Remember that we have done this exercise earlier. Okay. So, from u v n we have got T v n, okay, right, and from or u or s, okay, and from there we have got function a. Similarly, we have got T p n, this is function h, and from here we got similarly we got t p n and we got a function g. So, from here we got a function g, okay. And now the question is that if you want to find out from here what would be t v mu, what would be the appropriate function. So, again we use the same Legendre transformation, okay, and this is going to be A, or sometimes we also write F. So, F is Helmholtz free energy minus mu times n, because we are changing n to mu. So, minus of mu times n, and this is the function which we are going to minimize. So, if you replace f by u minus Ts, then this becomes u minus Ts minus mu n, this is nothing but minus Pv. Okay. So, so we can try to minimize this by considering u as average E, okay, as we know the expression, and n is of course fluctuating all the time. So, we have to worry about that as well. So, what kind of constraints we are going to put? Let us assume that we are going to put u as average E, and the particle number n is the ensemble average over macroscopic number of particles in the system, which can vary from 0 to m0, which can vary, which is arbitrary, because m0 could be extremely large. So, the n is nothing but average of n. So, remember that the particles can change, because you are not fixing the particles, okay, you are fixing only the chemical potential. So, it can vary, you can have also almost 0, there is no particle inside, and you can consider extremely filled system, and this will have different probabilities. Okay. So, all of them will have T, V, mu as external conditions. Okay. Now, with this we can consider now this function as this, okay, and if you want to differentiate this in order to get the minima, then we are going to consider d of f, or in general d average E d T ds minus mu d average m. And the constraints are: the probability must sums to 0, the energy summed over energy levels and particle number must give the appropriate energy average of E, the number of particles summed over all the states of the system must equal the appropriate particle number average of m. Now, without going how it is done, what we are going to do is write down the expressions of the thermodynamic properties and connections to the partition function of this particular ensemble. Okay. So, so you can write down this constraint in this way again. Okay. The double summation is basically for simple reason that for each m state, that means for each particle state, because the particle state, let us say in this case it may have different energy levels. Okay. So, it may have different energy levels, similarly for others may have different energy levels, and hence you are summing it up the probability of mj, which is the system has m particle and is energy level j, and you are summing up from j is equal to 1 to Tm corresponding to energy level m, and then you are summing up from m equal to 0 to m0. Okay. Similarly, you are getting the average E by multiplying EMJ and multiplying by the PMJ, okay, and then you have double summation, and similarly for delta m also. So, these are the constraints written in this form. Okay. So, you need to solve that, and after solving this, using the Lagrange multiplier, we get the grand canonical probability distribution as simply e to the power minus E m j divided by k t multiplied by E m mu by k t divided by this partition function. The partition function is double summation of this multiplication of exponential terms. So, this is nothing but Boltzmann factor, and this is the term which connects the particle and the chemical potential E m mu divided by k t. Okay. Using these expressions, we can connect in a similar way as we have done for canonical ensemble this expressions, which connects the u to grand canonical partition function. Remember that earlier the u was connected to the canonical partition function, which was q. Okay. And similarly n, because n is a variable and n is basically fluctuating. So, you can find n with the partition function p and n. So, n is basically the variable here. Okay. So, with this we can connect the thermodynamic property and the partition function. Now, as I said, I have not gone into details how to do that just because it is not a statistical mechanical course, but it is important to understand how this has been derived and how we can make use of it by doing a very simple example. Okay, so that was the intent for my side to give a exposure of statistical mechanics briefly. Now, so hopefully you understand the complexity as well as you can appreciate the beauty of this aspect of the the thermodynamics, where we connect statistical mechanics to the macroscopic property. In order to further understand this without going too much in details, what we are going to do is we are going to quantify the different models which we use it in thermodynamic to express the properties of the fluids. Okay. So, that means we must understand the intermolecular forces and the models. So, that will be the subject of this course in the next few lectures. So, we will see you next time with a new topic here. Okay.